your day, right? Tomorrow you're going to take a test. I was just looking at it and I haven't like pared it down to get exactly right. My guess is that it will be all or almost all multiple choice, but all or almost all of it will be AP multiple choice.
So like, do we have to explain our answers?
So I will probably ask you to explain your answers, which will be to your advantage. Do you know what I'm saying? Okay. Because if you don't explain your answers, then there's no way for me to give you partial credit. Do you know what I'm saying?
I don't understand.
So like if I just ask you to fill in bubbles, then, and there are 8 questions, then it's either right or wrong.
Okay.
Whereas if there are 8 questions that I ask you to explain, I don't need like a 5-paragraph essay.
Just write something.
But you can write down your explanation, and then if you get the answer wrong, but your reason, like you're doing physics that makes sense, then I can give you some credit for it. Does that make sense?
Yeah.
Do you see what I'm saying? So the reason that I ask you to do that when we're doing these, especially when we're doing just a few problems, is so that I can get into your brain a little bit more. Yeah.
What if we don't know how to explain something and we just put it down? Like, what if we just pick one?
I don't know.
Okay, all right.
What's up?
Are there going to be calculation-based questions, or is it going to be purely conceptual?
So there could potentially be calculation stuff, but generally, and I have not looked at the test very carefully. Like I've looked through it, and I don't think, and if you guys are working later today, I can kind of peek through it a little bit more. Anything that's like really calculation, there wouldn't be anything that would be really calculation heavy. Does that make sense? Like it might be like ratio kind of stuff, but it wouldn't be like, given this mass and this radius and with all of these different things, what is the moment of inertia? Probably not. No, but the reason that we do those harder problems is so that you then know how to approach the more conceptual ones. Some people find the conceptual ones more difficult. Some people find them less difficult. It depends on how your brain works, to be honest. So, go.
Can we lose points for writing something down? That's not the same as our answer.
Yeah, probably.
Okay, great.
Like, let me put it this way. You can't answer you bubble in letter B and then you answer the answer that would go for letter C. Like that seems like you're double dipping, and no. Do you know what I mean?
Yeah.
But if you bubble in B and you're writing work and B is not the right answer, let's say, and you're writing work that is right, but then you end up at the wrong thing.
I'm worried about the opposite. Like, what if you put in the right answer? I'm like, we don't know how to explain it.
Then it's just probabilities, my friend. I appreciate your honesty, though. Yeah. All right. So my plan for the day is very open. I do not have any this is what we must do, because I feel like most of the time when we have been reviewing for a test or whatever, it's been more productive for you to run the show. I would remind you about this sheet that we did last time, right? And maybe filling in the other side. This is going to be a really good guide to what we know. Okay. This really, if you were going to have received a study guide for this unit, this is what it would look like.
Okay.
Does that make sense?
Yep.
This is the content that we've covered, right? We've done more stuff than just write out equations, but this leads you to where you need to go. Kate, are you okay?
Yes, I'm good.
Are you sure? It looks like you're really uncomfortable. Well, I recorded everything, so there's that.
Yeah.
And I have a sheet for you over here somewhere. I'll find it for you. And if we need to adjust, we can adjust. It'll be okay. But here, you can have this pink sheet. Then you'll be cool like everybody else with a pink sheet.
Oh, yeah.
You're welcome. So I'm giving you the opportunity now. What homework questions do you have? That's what I'm at. So I'm just going to start talking, or not talking. I'm going to stop talking. And I see some hands, and let's just write down some things, and then we'll do it. Go. Chapter 7, problem 63. Is that what you said?
Yeah.
Elizabeth.
You didn't do all?
And what did you say? And 50.
Yeah.
Okay. Elizabeth, did you have one that you wanted to add to the list right now, or not yet?
Not a specific problem. Just if you have a propeller that's just one thing,
Yes.
you split it in half and then do the math for both sides and then add it up.
No, you use the. I have to find my thing here. Where did it go? Where did I have that? I don't know where it went. Where did we do these, guys? Here it is. It's this one. Slender rod axis through center. Does that make sense? Yeah. Yeah. I'm going to pull this down because I like it and we might need it later. Copy. Paste. All right. So I'm going to start on these questions that Ian gave me. Bring more as you have them. We'll just talk, and then when we're done, we'll just study. I mean, like, this is your day. You want to add one?
Yeah, I'm trying to find it.
Okay.
I think it's, I don't remember which chapter, but number problem 3.
Okay. Mystery problem 3.
There's chapter 8, problem 3.
Chapter 8?
Yes. Just need a boost.
Gotcha. Sweet. Okay, so let's do the chapter 7 ones first. Not because there's one that's better than another, just because that's where we started, and then we'll just cruise. All right, chapter 7, problem 63. Here it comes. All right. Chapter 7, problem 63. Okay, it says, a car with 58 centimeter diameter tires accelerates uniformly from rest to 20 meters per second in 10 seconds. How many times does each tire rotate? Does that sound right? Like that's the right question? Okay. All right, so let's start off. Where are we going to start off? Anytime we're stuck and we don't know what to do. Let's do givens first. Is that okay? And then we'll draw a picture. I like both of those things. So it says that the diameter of the tire is 58 centimeters. How often do I want diameters? Never. What do I really want? Radius. And what's the radius going to be? I hope you can figure it out. 29. And I'm going to put it in meters, right? Because meters make us happy. So that was going to be 0.29 meters. Is that okay? Everybody good there? Sweet. All right. It accelerates uniformly from rest. So that means that the initial velocity is 0 to a final velocity of 20 meters per second in 10 seconds. And they want to know how many times does each tire rotate? So really, what are we looking for there? The number of revolutions and revolutions. What is that measured by? What thing do we use to measure revolutions? Like, what is that? Is it radians per second? You're close.
No.
Yeah, it's just the angle, right? Does that make sense? So it's kind of like we're looking for theta. Or like how many full circles are we doing? There are lots of ways to do this. I don't know which way you want to start. So somebody start me. By lots, I mean like 2 or 3, not like an infinite. I guess some mathematicians would argue an infinite number of ways. I don't want to get into that today. How might you start? Nick, you seem like you want to say something, but maybe not.
Well, I don't even really remember how I did this, but I ended up finding the distance, and then I also found the circumference, and I did distance divided by circumference.
Cool. Seems like a reasonable way to do it. Do we have an equation that has initial velocity, final velocity, time, and linear distance? Do I need the acceleration? I mean, it is accelerating.
Acceleration would just be 2, because you have time and you have the change in velocity.
So we could do that. Do we not have, I can never remember which equations they actually give you, because there's one without acceleration in there, but they don't give it to you. Okay, never mind. Yeah, so let's find the acceleration. Let's do it. So acceleration is change in velocity over time, which is 20 meters per second divided by 10 seconds. So 2 meters per second squared. Is that okay? So then we got everything we need, really. What equation do you want to use, friends? I don't care. Everybody's favorite? What do you want to use, Ian? Okay. So that would be the Vx, or the V final squared equals V initial squared. Yep. And so this is all still just translational stuff, right? We have not introduced any Greek letters. We could have said, this question could have been in chapter 2 or whatever, right? A car starts at 0, it moves it goes 20 meters per second after 10 seconds. How far did it go? You've done that problem. Maybe not exactly that problem, but you've done that problem, right? Solving this for D. Okay. You can also use the big, long, scary one. I put that in big air quotes, right? D equals VIT plus 1/2 AT squared. Same deal. Same stuff. Either way, what do you get for the distance that the car travels? Did you get a value? Okay. Thank you for throwing that out there. So the final velocity squared minus the initial velocity squared over 2a. This is question number 63 from chapter 7. Can anybody corroborate what Nick said? So D is equal to, what'd you say? 100? Okay. So now we know that's a distance of 100. So if we think about that, if the wheel starts here, and I'm going to start it from the bottom. Let me make my little mark on the bottom. And it starts to roll this way, right? In one revolution, how far does that wheel go? It's circumference, right? Circumference is 2 pi r. So that's going to be 2 pi times 0.29 meters. So you could figure out how much one circumference is. And if you know that this thing has to go 100 meters, then the number of revolutions is just going to be the distance divided by the circumference. Is that feeling okay? Cool. Should we plug in some numbers here? So 2 pi times 0.29, what do we get for that? What is it? I hear lots of people speaking quietly, and my ears are not good today.
I got 1.82.
Thank you. I'm not gonna leave things in terms of pi. Okay. Not today. So then we're gonna take 100 divided by 1.82. Okay. So the distance of 100 meters divided by 1.82 meters per revolution will give us the number of revolutions. Is that all right? Okay. What'd you get, Courtney?
54.95.
Thanks. All right. Close to 55 revolutions. Is that okay? Sweet.
I thought.
Nice job, team.
I get confused on because I tried to go rotational kinematics from the get-go, so then I kind of confused myself.
You totally can.
Okay.
Do you want to talk
I got
through?
the wrong answer.
Oh. Well, my guess is that there was one little mistake somewhere, right? So you have your radius. So every time you have your radius, then you you can convert everything, right?
Right.
So velocity is equal to r times omega.
Right.
So you're going to take the 20 divided by that to get your omega.
Mm-hmm.
Your time obviously doesn't change.
Yeah.
And so then you can find your alpha, which is going to be your change in omega over time. And then do the same thing. And you can actually work through it. One could do this if one wanted to. And the r's just cancel each other out. Yeah. So it will work.
Okay.
But sometimes it feels a little bit funny doing that.
Okay.
Yeah.
So it is fine.
Yep, absolutely. Yeah, as long as the one thing you want to be careful of is not to mix them. So you got to go all translational or all rotational.
Okay.
Yeah. I wouldn't try and bounce back and forth because that gets messy.
Wait, while we're close, can we do in that same? I just had a question on D of number 12.
Number 12?
Yeah.
Sure. And then we'll come back to number 50.
Okay.
Is it problem 12?
Yes.
Okay. The Earth's radius, that one?
Yeah.
Earth's radius is blah, blah, blah. It rotates once every 24 hours. What is its angular speed? And you said you want a D?
Yeah.
What is the speed of a point on Earth's surface halfway between the equator and the pole? Okay. So talk to me now that I've read the question.
Okay, so I didn't get that at all.
That's okay.
So point. What is it again? Between the equator and the North Pole.
Yep. So, okay, so here's
It said something else.
the Earth and it's spinning like this, right? So if here's the equator, there's the North Pole, obviously. So halfway between is going to be somewhere like here, right? And so it's rotating with a different radius. So the angular speed is going to be the same, but the tangential speed is going to be different. So this is kind of like the lion and the horse on the carousel problem. Does that make sense?
How? Is it like so?
Yeah, keep talking.
So it's going. Okay. So we're trying to find. Maybe I was confused about what we were looking for.
You're okay.
So we're looking for what exactly?
So this is the radius of the Earth here.
Yeah.
I'm just kind of put in what we know.
Which is the 5 or the 6 point something times.
Yep, 10 to the 6th. Mm-hmm. Yep. And then you know its frequency, right? It's one cycle every 24 hours. And then it says, what is the speed of a point? So they want to know, so this is part D. They want to know the tangential velocity at a point halfway between the equator and the pole. So if you think about that, if you're sitting right on the pole, then your radius is 0, right? Because you are right next to the axis of rotation. If you're way over here on the equator, then you're traveling a whole lot further. So even though your angular speed is the same, your tangential speed is a lot higher.
Okay.
So if you're halfway between, then we need the radius here. So you're going to take the radius that it gave you, divided by 2, because that's going to give you the radius here. And then you've got your frequency and you've got your radius. Is that okay or no?
Sure.
You can absolutely say no. That's totally fine too.
Yeah, I think I'm good with that.
Okay. Yep. And then that'll give you your tangential velocity because you know your omega, right? Because omega is 2 pi f.
Yes.
Yeah. Do you want me to keep talking or are you feeling okay?
Yeah.
Okay. All right. Sweet. Good questions, you guys. So that was number 12. We did 63. We did 12. 50 was the next one. All right, number 50. Ooh, the engine in a small airplane is specified to have a torque. I'm just going to start writing my givens down now because I'm guessing we'll need them. Has a torque of 500 Newton meters. The engine drives a 2 meter, so this is kind of what Elizabeth was asking a minute ago. A 2 meter long, so that's going to be the length of it. Bless you. Yeah.
Yeah, that's this problem.
Oh, look at that. So you're set to go? Or do you want me to keep doing on it? Oh, okay. Sweet.
You can keep going.
Oh, I will keep going. Absolutely. So this is, I noticed that when I was doing the problems that I handed you on Friday, the angular momentum problems, they were from the book also, because I usually pull questions from books that I'm not using. Obviously, when I wrote those problems, I was using a different textbook. So there you go. This was like my go-to book for answers.
So for the propeller,
Yes.
I can know which one to use.
Yes. Yep. So hold on just a second. Let me write all my givens down and then we'll totally do it. Hold on just a second. So 2 meter long, 40 kilograms, single plate. So that's the mass. Oh my gosh. Okay. On startup, how long, so we're looking for a time, does it take for the propeller to reach? Oh my goodness gracious. I'm just going to cry and start using markers. I mean, not literally, but I'm just crabby.
I think there's something wrong with those pretzels.
There is. The connection is really bad. That's why when you hit it, it resets the, yeah. Which is why I've got all these little like bang marks. It's pretty fun. Yeah. But we don't have enough, like, you have to buy a whole new computer because
Like all the teachers.
maybe I should. I know, right? It's awesome. Anyway, okay. 2000, maybe. One of my ninth graders has been starting a tally sheet to count how many times I do it in a day. It's pretty adorable. Now, I told her that she needed to like also time the amount of time that I was actually doing notes. She's like, that's too much. It's like, well, you need to know rates. Like, I feel, but she's not quite to calculus yet, so she doesn't quite get that. What is that 2,000 RPM, by the way? What is this a measure of? Like, what would I put equals here?
Equals the
4,000 higher.
I didn't do that.
What's that? Rotations per minute. So what is that measuring? It's an angular velocity just in funny units, right? Yeah, so we'll change the units in a minute. Okay. All right, so we need to know time. So the first question was, which one of these are we talking about? So we're talking about a propeller, a single blade propeller plane. That's this slender rod axis through center. So I will say this again. You do not have to have these memorized. You do not have to know where they come from. If you want to go through that with me, just let me know and we'll do calculus anytime because it's just a nice cute little integral. But for now, all you need to know is where to look for a problem. On a test, it would give it to you, okay? Or it would give you like a little chart with them if you had to apply them for different ones, okay? So it's this one, it's 1/12 ml squared. So moment of inertia for this situation is 1/12 ml squared. Okay. Now what? How am I going to do this problem? You get started? Sure.
I found rotational acceleration.
So we need to find the rotational acceleration. That's marked with what letter? Alpha. And how are we going to find alpha? Yeah, Newton's second law, right? Okay. So I know the torque, and I can find the moment of inertia. So that's torque over 1/12 ml squared. Okay, so I've got all that stuff that I need. And once I know alpha, now I need to find time. How am I going to do that? This omega is really the final, isn't it? Yeah. What's the initial omega? 0. I know alpha. I know omega initial and omega final. Do I have an equation that has those three things in it? Indeed, I do. Right? I know that by definition, alpha is equal to omega final minus omega initial divided by time. So time is equal to omega final. Omega initial was 0, so that's kind of unexciting. Divided by alpha. Rotations per minute, how do I deal with that? So let's do some conversion, right? This is just unit conversion. So this is rotations. I'm going to write it out. So if it gets scary, it looks intimidating to you. Just look at it. So a rotation is going to be how many theta? Or how much theta? One rotation? 2 pi. So it's going to be 2 pi radians in one rotation. Times 1 minute is 60 seconds. Okay. So that'll give you your omega. Sorry, this kind of ran into the other. Okay. So 2,000 times 2 pi divided by 60 will give you your omega in radians per second, which is more reasonable for our purposes. And then we're just going to plug stuff in. Okay. This is a nice problem. I'm not saying, sometimes I say that, like when I'm telling you what's going to be on a test. I don't mean that in this one, but I like this problem because you have to kind of put some things together, right? You have to put your Newton's laws with your kinematics. But this is all stuff you guys can handle. It's just a couple steps. Are we okay with this one? There was one other question that we had brought up. Chapter 8, problem number 3. Chapter 8, problem 3. I wanted to say too, I can't remember if I emailed you all or not. I don't think I did. I did put all of the solutions for chapters 10 and 11 up as well, so you could get the energy and angular momentum stuff. So hopefully you saw that. I think I got it done yesterday at some point. I apologize for the lateness, but I did it because somebody asked me for it, right? Send me an email and it happens. Yeah, might take a couple moments, but yeah. All right, problem number 3. Oh, is this the one with the guy on the table, Courtney? Is that the one you're talking about?
I just didn't know how to set some of it up.
Yeah. Shall we do it?
Yes, please.
Mm-hmm. Let's do it. Whoa. Chapter 8, problem number 3. Okay, so it says, how close to the right edge of a 56 kilogram picnic table can a person stand without tipping the table over? Okay. So this is, and I don't mean this in a like dull way, but this is very similar to the cantilever problem that we did, the applied problem, right? So let's take a look here. So here's the table. It's a big table today. I don't know. We'll put it on some ground. And a purple person.
The tabletop is obviously not fastened to each of the legs. So
What's that?
the tabletop couldn't possibly be attached to each of the legs.
What do you mean? I mean, I think it's going to tip right here, isn't it? This is going to be the axis of rotation. Right here, right?
No, it's just that physics problems have a way of doing it.
Of being goofy. I think the axis of rotation is going to be there, isn't it? I mean, I don't walk on picnic tabletops a lot, but I think that's what I would imagine would happen is this person. Whee! They're wearing a hat. Because why not? Awesome. All right. Free body diagram, right? First thing to do, free body diagram. What am I going to do? What forces are acting? Gravity. Gravity acting on what? On the person. Which way is it pulling? Indeed. So I'm going to call that the force of the earth on the person. I'm going to call that FP, just to be different from the others. Is that okay? You can call it FG also. That's fine with me. Any other forces acting? Gravity, yeah. Yeah, of course. Where's that pulling? Yes, agreed. It is pulling down. Where is the center of mass of the table? Where can we assume that all of that force is going or pulling from? The middle of the table. I think unless they say otherwise. So we need to write down a couple of things here. So we know that the table is, it says 2.10 meters long. So that means that the force of the table is going to be right here, right? I think that we can, that's a good question. I think that we can assume that it's uniform unless it says otherwise, because otherwise the answer would be cannot be solved. Then your answer will not match the answer in the back of the book. So it's going to be the force of the Earth on the table. I'll call that Ft. Is that okay? Not to be confused with the tension force, but you know. All right, and
Normal force.
hey, a normal force.
Yeah.
Now, how many normal forces are going to be acting right at the moment where it's just starting to tip? Say it with confidence, Courtney.
One.
Yeah. So if he's standing right in the middle, then both legs are going to be pushing, right? For sure. Like the Earth is pushing up on both legs. But as he moves further and further and further and further over, the force here on the right, or excuse me, on the left-hand leg is going to get smaller and smaller and smaller. You with me there? Like it's going to go closer and closer and zero. And so it'll only be the force right here at that tipping point, if you will. So we're going to call that up this way, the force of the ground on the table, Fn. Okay. It also tells us, sorry, this picture is getting a little bit full, but it tells us this distance here, which is helpful, is 0.55. That's helpful both for that and to figure out this distance, right?
Mm-hmm.
So if this is 210, then this is 210 divided by 2, 1.05. And I've got 0.55 on this side, so how much is left over here? 0.5. All right. Now I've got a lovely picture. Now I can draw, or I can write free body diagrams, right? Or excuse me, write F net equations and torque net equations. Let's start with the torque one, shall we? Net torque's got to be equal to? Zero. We're going to add up all the torques. How many torques are there? 3. For every force, there is a torque. So there's a torque from the Earth on the table. There's a torque from the normal force, and there's a torque from the person. All right. We know everything we need to know about the person's force and the person's distance, right? So we don't want to get rid of that one. We don't know the distance here, so we need this one. Got to hold on to that one. We know everything we need to about the table, don't we? We know the force of it. We know the distance, so we want to hold on to that one. Do we know the force that the Earth is pushing up with? Do we care? We do not. The thing that they want to know is the distance that's sitting in here with the person. That's what they want to know. They want to know, let me put one more line in there. They want to know this distance here. Okay? So let's get rid of that one. Now, can you solve this putting your axis of rotation somewhere else? Yes. You would need your force net equation and your torque net equation. You need to do a system of equations. I mean, some people enjoy that, but why make it harder than it needs to be? You know what I'm saying? So, here we go. The force, let's just write this out. Let's just do it. The mass of the table times g, that's the force, times that distance, which is 0.5 meters, plus, that one's gone away. So this is the mass of the person times g times the question mark. That's what we want to know. So we'll call that r sub p. This is our big question mark. If you have two things that add up to 0, what do we know about one of them? They have to be equal, and one of them has to be negative. Which one in this case would be the negative one? This one? This one? Because it would cause it to turn this way? Yeah. Does it really matter? No, we got to pick one that's 0. Or excuse me, one that's negative. I'll make this one negative. So we can say the mass of the table times the acceleration due to gravity times 0. Come on, team. Has to be equal to the mass of the person times gravity times the radius. Again, this is the thing we don't know. So you can be like Gunnar and use G is 10. You can be like anybody else and use 9.8, or it does not matter, does it? In this case, bye-bye, G. Right, this is why we don't like to plug numbers in early, because those G's are going to go away. You with me there? Okay, so now let's look and see what we know. How close to the edge of a 56 kilogram table, so 56 kilograms times 0.5 meters, oops, equals, how big is this person? 70 kilograms times the radius of P. Does that sound okay? Do some algebra. By that I mean multiply and divide. What else can I do to help?
Number 4 from the angular momentum.
Sure. Can you make sure we're good on this one? Oh, go ahead.
So when you drew the why is there another place after the person?
There is, but that would be an internal force. So there's a force of the table on the person, there's a force of the person on the table. Does that make sense? But neither of those is going to cause that system to rotate. That was a very good question. Did you guys catch Rosanne's question? She said, why didn't I draw a force of the person, or the normal force of the table pushing on the person?
Right.
And the answer for that, and this is something I've kind of swept under the rug, and I apologize for that, is that the forces that we're drawing for this system are only external forces to the thing that we're calling the rotating system. So in this problem, as this guy walks out to the edge of the table, if it rotates, the table and the guy, that whole thing, those two objects are going to rotate together. Does that make sense, at least for a moment, and then maybe he'll fall off or whatever, who knows? Okay? But, so the only things we care about, so I've been kind of lazy about this. This is really the force of the earth on this part of the, on part of the system. This is the force of the earth on the other part of the system. And this is the force of the ground on the system. The other one, like the force of the table on the person, the force of the person on the table, that's an internal force. And remember, internal forces are not, this almost sounded really dumb. Internal forces are not external forces. That's true, right? They're not going to cause an acceleration. Okay. Does that help a little bit? Does that make sense? It was a really good question. That's awesome. I feel like I saw another hand somewhere. Yeah.
So wouldn't the axis of rotation in that one actually be in between the flat part of the table and the legs?
Like here?
Yeah. Because of the radius that you use.
Maybe. But the beauty of it is that it does not matter. You can set it wherever you want, right? And it's kind of like when you have the frog and you pick your height. As long as you are consistent, it doesn't matter. You could set, I've had many ornery students over the years who have wanted to try and prove me wrong about things. And this always comes up. They're like, well, I want to put the axis of rotation over here. Okay. You do that. And so then we do this problem, and then we do like 3 more problems, and they're like, oh. Because they have to set up a torque net equation, and they also have to set up an F net equation because you don't know this force. You with me there? But you have 2 equations, 2 unknowns, you're done. You can solve it, and you're going to get the same answer. Yeah. It's kind of So if you want to prove that that's true, knock yourselves out, but I'm not going to take time to do that. Other questions on this one before we move on? Okay. Ian, you said number 4 from this thing? The Joey one? Okay. You're like, I've seen this problem too many times and I'm still mad at it. I think this is actually in your book also. I think it's one of the example problems. Yeah, because when I was flipping through, I was like, oh, there it is. But anyway, let's totally do it. So angular momentum is always conserved in a closed system, isn't it? Yes, it is. So Joey, whose mass is 36 kilograms, stands at the center of a merry-go-round that's rotating once every 25 seconds. Did you guys have merry-go-rounds when you were in elementary school still at the playgrounds or no? were they taken out because they were
Yeah,
too dangerous?
safety, whatever.
Blah, blah, safety,
There's
blah,
some
blah.
parks in Iowa City.
They are, because yeah, we went to a bunch of parks this last summer and my kids,
They
I'm
are
like,
kinda
sit
dangerous.
down. They really are.
Really, that's
They are. And you know, so then if you go with my children, they're like, angular momentum. I'm like, you got it, girl. It's awesome. All right, anyway. While it's rotating, Joey, or insert one of my children's names there, walks out to the edge of the merry-go-round, 2 meters from the center. What is the rotational period of the merry-go-round when Joey gets to the edge? Okay, so we just need to kind of do a before and after, right? So if we imagine, so I'm going to draw this from above. So there's the merry-go-round. So at the beginning, Joey's right there. Joey initial. And then at the end, Joey's over here. Final. We know that the angular momentum of the system has to be conserved. So that means that L total at the beginning has to equal L total at the end. So you remember on Friday when we were doing the little spinny thing with the weights, right? We didn't actually do the math with it, but one could. It was like one person with the 2 weights. In this situation, we've really got 2 things. We've got the merry-go-round itself, and we've got Joey, right? So let's add them together. So it's the angular momentum of Joey at the beginning plus the angular momentum of the merry-go-round at the beginning has to equal the angular momentum of Joey at the end plus the angular momentum of the merry-go-round at the end. Okay. Do you remember from Friday? How do we quantify the angular momentum? L equals, what was it? Times omega, right? Yep. So then we're just going to do that. So we're going to write it down. So here it comes. So we're going to have I for Joey at the beginning plus omega at the beginning plus I for the merry-go-round at the beginning plus omega at the beginning. It's kind of gross, but I'm just going to write it out just to be as clear as possible here. Okay? That equals I for Joey at the end times omega at the end plus I for the merry-go-round at the end, omega at the end. Now, I could have put one extra set of subscripts, but that sounds like a horrible plan. How does omega at the beginning compare for Joey and the merry-go-round? They're the same. Does that make sense? They're spinning with the same number of rotations per second, okay? Same for the end, okay? Does the moment of inertia of the merry-go-round change? No, it's the same all the time. So the only thing that changes is the moment of inertia of Joey. We're going to assume that Joey is a point particle. Okay, let's keep it simple. Okay, like I don't want to know, like, who cares about the rate, whatever. It's just going to be a point. Okay, and so what do we need to know? How do you quantify the moment of inertia then for that point particle person? mr squared, right? So we've got the mass of Joey times the radius of Joey squared plus, let's cheat here and find out, where is it? Where's our disk? Our disk is going to be here, so that's going to be 1/2 mr squared. That's this thing right here, right? Oops, nope, we want to here. I think that was right. There it is. Same deal over here. MJRJ squared plus 1/2 MMR squared. That's an M in there too. Omega final. What are we trying to find here? What is the rotational period? So really we're looking for omega final, right? Because once we know the angular frequency, we can find the rotational period. And really the only thing that changes is the radius, and the radius causes omega to change. Okay. So I think we know everything in here except omega final. then I think we can solve it. Do you want me to keep going, or does that get you where you need to go? Keep going? Okay. So let's see what we know here. So we know Joey's mass. We know the merry-go-round's mass. We know that it's rotating. Oops, I'm going to do this down at the bottom here so we can talk about it. Once every 25 seconds. So we know that omega is related to 1 revolution every 25 seconds. So we can say that that's 2 pi radians in 1 revolution. And so we can find that's our initial omega, right? And what's that? Oh, 2.5 seconds. Yeah, 25 seconds would be ridiculous. Sorry. Yes, thank you for catching my miswriting. And so walks to the outer edge of the merry-go-round. So the radius of the merry-go-round is 2 meters. So the radius at the beginning is 0, isn't it? So that means that this is 0. So this one is 2. And then we just got to plug numbers in. Yeah. It is. It's true. Yeah. Does that get you where you need to go, Ian? Cool. Cool. So again, a problem like this, I wouldn't ask you to flesh all this out in one multiple choice question, right? Like that's not going to happen. But understanding what would happen if Joey walks from the middle to the outside, right? And maybe why, right? That's the stuff that I really am going to be interested in looking at. Okay. Did I miss other questions? Do you have other questions you want to talk about? We've got about 8 or 9 minutes. Why don't you spend 8 or 9? No, is that right? 3:05? Yeah, 5, 6, 7. Yeah. Why don't you spend a few minutes doing physics? I know that's a lot to ask sometimes. Okay, but I don't care. So no phones are out. Get some homework out, or get some problems out that you haven't finished, or get some problems out that you have finished, and look through them again. Get out that pink sheet and look at it again. You've all got something to do. Okay? Take a few minutes. And if you come up with more questions, I'm super happy to answer them. Just let me know. Okay? But don't waste this time. Don't make this just I'm going to turn my brain off time. That's not okay. I mean,